of an astronomer audience, right? And so I want to say from the start that this talk is going to be of no use whatsoever to you, right? Or possibly to anybody else. And on that basis, I would like you to pay attention, right? So it's a purely an attempt. So you see, it's just started getting recorded. So this is not on record now. It's an attempt to talk a little bit of classical physics, purely for entertainment. And we are, I mean, given the weather outside, we are clearly in need of some entertainment. And so let's do that. I also hope that what I'm going to be talking about. In fact, I don't hope, I know that what I'm talking about does not require any particular specialist background. It's all undergraduate physics, and it was pointed out to me yesterday at dinner by some of your colleagues that in France, it might not even be undergraduate physics, it might actually be school physics, right? Or possibly kindergarten. I don't know. What is class prépa? That's kindergarten, right? Anyway, so we'll sort of start from nothing and try to get somewhere. Whether we'll get somewhere, we'll see. This is, I should say from the start that I owe the majority of what I'm going to talk about, at least results-wise, although possibly, in fact, certainly not the confusions, to the three students with whom I worked on this, Toby Atkins, who's just graduated and went off down under, to continue his research in New Zealand. Robbie Ewart, who's actually sitting right there, he came along because we were worried whether anybody would turn up for this colloquium. And so, ever since COVID, we know that if you want an audience, you bring it with you, right? And so there's so Robbie's sitting there, and he's responsible for the majority of it, of the good things in it, and Michael Nastak. Why doesn't it? How do you? Okay. So, right. So what I'm going to be interested in is a kinetic description of a collisionless plasma. What does that mean? It means basically a bunch of particles experiencing a force, in plasmas, unlike in galactic dynamics, those of you who have a background in galactic dynamics might be thinking about that. So in plasmas, we make a distinction between what we call collisions and what we call interaction with fields. That distinction to a galactic dynamicist is very unnatural. Because by collisions, of course, we don't mean that hard objects smash into each other and bounce, like that is supposed to happen in neutral gases. What we mean is still Coulomb interactions, but those are Coulomb interactions that on distances that are much smaller than the Debye length, the screening length in a Coulombic plasma, and that is the main distinction between galactic dynamics and plasma physics on the face of it, right? That electric field can be charges can be screened and gravity cannot be. So if you like, from our point of view, everything that happens in a galaxy or in any combination of mutually gravitating objects, all of that stuff is constantly in a state of collision with each other. Or if you like, all of it is completely collisionless. And for galactic dynamicists, that's the same thing. For us, we put away binary collisions between particles. They can be one can estimate how often they happen. They can be infrequent in comparison with other relevant frequencies in the system. And that's what we mean by collisionless plasma. And so mathematically it just means that there is this equation which describes these objects, and we pack all we coarse grain it essentially on the Debye length. We pack all the collisions into the right-hand side, and then we cross it out. So also for simplicity and for closer resemblance, if you like, to gravitation, I will think of my electric field as being electrostatic, so as being a gradient of a potential. And there's going to be no magnetic field in this talk at all. So the result of that is called in our business is called Vlasov's equation. So this is what it is. F is the distribution function of the particles. It just describes streaming and interaction with the electric field, and the electric field is described by the Poisson equation. Now, I'm gonna think about plasma containing only electrons, and the ions are going to sit still in the background and provide a neutralizing background for the whole thing. So it'll be a one species situation. Now, the first thing that I want you to observe about such a dynamics. This is just, when I said it's on the class prepar level, right? What you really are looking at is just the Liouville equation. So phase volume is conserved, right? Like we learned in classical mechanics. And if you like, the sort of a mathematical description of that, or a mathematical description of that would be, if I took any function of the distribution function and integrated it over the entire phase space. By phase space, I mean R and V, positions and velocities. That would be conserved by dynamics, right? So d by dt of this is conserved. So there is an infinite, continuously infinite set of invariants, which some people call Casimir invariants in this context, that constrain the dynamics of such a plasma. So I am going to the form in which I'm going to impose those constraints is the following. So there's this little piece of mathematical description. Let's imagine, rather than taking arbitrary functions of the distribution function, I'm gonna make them delta functions. So I'm gonna imagine a delta function that is a function of a certain parameter, which I will call eta, and that delta function is going to be a delta function of the distribution function minus that parameter. So if you like, it's a kind of density in phase space of places where the distribution function is equal to a certain, a volume in the phase space of where the distribution function is equal to a certain value, right? And there will be a continuum of these values, and if I now take this thing and integrate it over the entire phase space, I get this function which I call rho of eta, which I will refer to as the water bag content of the distribution. We'll see in a moment why I call it the water bag content, but that's just notation. Now, so I'd like to think about what happens in such a system. Now, obviously, if there is no electric field, nothing happens in the sense that any distribution function that is a function of velocity but not position is going to be in equilibrium, right? And nothing will happen in a way. Nothing interesting will happen, at least. Now, however, if you took such an equilibrium, or any kind of equilibrium, meaning just a fixed point of the equation, and if it turned out to be unstable, which the majority of equilibria are, that would create perturbations. Perturbations will create electric fields. Electric fields will start moving things around. The whole system will eventually move towards some kind of stability. If that involves disappearance of all fluctuations, then everything would freeze. If the fluctuations are still there, but the distribution function is stable, there's some kind of evolution that is still continuing in a way that we don't fully understand. The question is, what does a distribution function of particles in such a system evolve to, subject to all these constraints on the dynamics, right? Now, let me first point out the complexity, or perhaps also then the simplicity of the problem. So what does this equation do? Well, it does two things. V dot grad f, the streaming of the particles, that's called phase mixing in velocity space. All that does is that if I had imagine you had a 1d plus 1v problem with just one spatial position and one velocity, and you put a little blob in there of particle distribution. And then you apply the v dot grad f to that. That's a shear in the xvx space, right? So that blob would get sheared over, and you would get a sort of a teased out thing like that, right? Like in the middle picture. The second term involves interaction between perturbations, the grad phi, or electric perturbations, and the distribution function. And so it involves some mode coupling in real space. So in what that's going to look like in on a cartoon level is that these teased out structures would get tangled up. So what you have is essentially phase mixing or phase refinement in phase space, in both velocity and position, of the part of the distribution function that depends on position. And the dependence on position is important for both effects. For phase mixing, there has to be a grad f. For the mode coupling, obviously things have to depend on space, and to have an electric field, you have to have a grad phi. Okay, so all of this served to demonstrate one, in many ways, very essentially trivial point, which is that I can think of any dynamics or any equilibrium in phase space as a combination of two things: a mean distribution function, and for simplicity, I will, one can talk about ensemble averages and so on, but I will just imagine a homogeneous box where stuff happens, and mean to me will mean mean over that box, right? So I'll take a distribution function, integrate it over volume, and what will remain will be a function of velocity, and that's what I call f bar or f naught. And that's a kind of a background equilibrium, and then whatever else is there is going to be called delta f. Okay, it doesn't necessarily have to be small. It's just the difference between the mean and the exact. So what you see on the two pictures on the screen is an example from a recent numerical simulation, not having anything to do with me. It was done a few years ago at Princeton by Valentin Skutnev. It's a kinetic simulation, two dimensions, two velocities. And these are two projections, one on two velocity components, and the other, so on the left, yes, on the left, it's the projection on Vx, Vy, and on the right, it's a projection on Vy and Y, right? So one spatial, one velocity component. What this is supposed to show you is that two obvious things. A, there is an overall shape, and B, there is a structure inside that shape. Okay, and that's the f bar and the delta V, and that generates two questions that an idle theoretical physicist can ask. One of which is, is there what are these collisionless equilibria? Is there universality there? I mean, you might take the view a priori that actually this is not an interesting problem because depending on what the initial conditions are, something different will emerge every time, and when something different emerges every time, that's really no longer physics, right? That's called modeling, I guess, right? So something different has just emerged in the morning in Paris. Different both from numerical simulations that showed that the sun would shine, and I guess from what will happen this afternoon. So it clearly all depended on the initial conditions. So, or perhaps there's some universality to it, like it always rains in Paris in September. Right. The second question, nominally a different one and an interesting one in itself, is what is the structure of that fine scale part of the distribution function? That's the question about the structure of plasma turbulence. Right. So delta F is the turbulence. You will see shortly that these questions are actually related to each other. The one about collisionless equilibrium and equilibria and the structure of the turbulence. So how to approach this problem? Well, we know in nonlinear physics and statistical physics, and maybe generally even in physics, that nonlinear problems are hard, that we don't know how to solve them, that outside perturbation theory there isn't very much we can do, and perturbation theory usually doesn't work, at least in our world. And so what is the scoundrel's last resort? It's to refuse to solve equations and instead do some statistical mechanics, right? So and that was if you like, the start, at least of this intellectual strand, which, as Clement mentioned, was due to Donald Lynden-Bell in the 60s, who was thinking of a similar problem in the context of stellar dynamics. This is, I should say, one of the rare but very spectacular examples where things happened in galactic dynamics before they happened in plasma physics, rather than in the opposite in the opposite order. It's plasma physics that had to take inspiration. Plasma physics did take inspiration. So Kadamtsov and Pogutse, in just a few years after Lynden-Bell, realized that this could work for plasmas and adapted it in a certain way. So here's how we're going to think about this statistical physically. So we take a phase space, which is just velocities and positions, and let's break it up into microcells of phase volume that I call delta gamma. And then I want to start by considering a distribution function that is extraordinarily simple. There's going to be an initial distribution function that in each of these microcells is equal to either 0 or a constant, right? And that's called in plasmas, I think also in galactic dynamics, this is called the water bag distribution, right? Water bag because you put water in a malleable elastic bag, and then the world is divided into the inside and the outside of the bag. And you can deform the bag in any way you like, but the water has more or less constant density. And so everywhere in the world, either there is a piece of water or there is nothing. And that's called the water bag distribution. Okay. So then what you do is you assume, I don't want to go through mathematical detail of it. I'll put them on screen. You can be staring at them while I'm talking. So you take these microcells, and you then assume that they mix completely randomly, and you assume that there are no barriers to this mixing. So everything is homogeneous, everything is nicely mixed. You assume that the probability of anything is equal to the probability of anything else, and so essentially you do the usual Boltzmann statistical mechanical thing. And if you do that, and if you then coarse grain in some way this set of microcells into macrocells, each of which contains lots of microcells, and with each of which you will associate an occupation number by filled parts of the water bag, you can construct a mean distribution function, coarse grained in this way. And you should think of the previous construction that I showed you, this F bar, which was integrated over the entire space. So you could think of the macrocells in our context as containing each macrocell contains the entire position space. No, everything's mixed. Everything's just mixing randomly, right? I have no idea what equations any of this satisfies and so on. I'm just assuming that whatever the equation does, it'll amount to moving them around randomly and chaotically, because we know that nonlinear world is random and chaotic, right? So I mean, of course, on the dynamical level, particles interact with fields interact with each other, all sorts of stuff happens. But I want to be agnostic about exactly what happens. Modular just saying everything's nicely mixed. And it turns out that if you do that, and if you then do the usual sort of undergraduate statistical physics of this, you will discover that there is an entropy, and by just counting the number of possibilities. And then then you maximize this entropy. You can maximize it subject to constant energy and constant number of particles, and you find a Fermi-Dirac distribution. Mathematically, it looks like a Fermi-Dirac distribution with two constants. It's right there, right? Beta and V. Beta and mu, the inverse temperature and chemical potential, and these things are fixed on the basis of requiring constant number of particles and constant energy. So it's not actually surprising that you end up with a Fermi-Dirac distribution, because think about what is happening with these little microcells. So they move around, and each of them can be anywhere in phase space, but there is a restriction. They can't jump on top of each other because phase volume is conserved. Remember that, right? So the Casimir invariants are there. So they are mutually excluding non-cohabiting particles. They satisfy Pauli principle. They are distinguishable, unlike quantum mechanical fermions, but that turns out not to matter in this context. Okay, so that's where it gets us. Just to give you some intuition for once we talk about Fermi distributions, what does every undergraduate have to learn for their exams, right? Well, there are degenerate ones and non-degenerate ones, and stuff happens differently depending on how degenerate or non-degenerate you are. Now, what does it mean, degenerate or non-degenerate, in this context? Well, it means roughly this. So here's a very, very, very simple example. So let's consider two possibilities. One in which our initial distribution is actually in both, the initial distribution will be two beams. And on the left, you have a case where the beams are hot. meaning that each beam, so a beam is just, well, this is a beam, right? This thing here, right? It means, you know, particles moving at a particular velocity. And the hot beams means that the beam has a width in velocity space, right? So there's a velocity spread inside the beam, right? And a cold beam is where everybody moves at the same velocity, right? And so there is no spread. So it's, if you then try to mix that around, what will emerge is something that looks very much like a top hat, like a, you know, degenerate Fermi-Dirac on the left, and something that looks very much like a Maxwellian on the right. And the difference between these two things is the following. So remember that the phase volume that the initial distribution occupies cannot change, right? And the energy cannot change either. So we fixed the energy, which means that if the initial distribution, so the fact that energy cannot change means that the amount of phase space available to you overall is effectively limited, right? Because, you know, you can't have a lot of particles at velocities that are much, much larger than the energy scale of the system, right? So it gives you a kind of a vague ball in velocity space within which you have to stay. And basically, if at the start you occupy a significant part of that ball, then you're degenerate, and if you don't, then you aren't. Okay? And so you can see that the distribution on the left takes up more phase volume within the phase volume that's available to it, and so the exclusion principle matters, and so you end up with top hat distribution, and the distribution on the right doesn't, and so you end up with a Maxwellian. So that's a simple picture of how one starts. But then you might say, that's all great, but and right, what is this Waterberg distribution? And nothing's ever a Waterberg distribution. Well, two beams, yes, but that's about it. Well, this is very easy to generalize. So I can now take my general distribution. Well, first I can make an obvious step, and I could say, well, no, let's consider two Waterbergs, right? So the probability of particles can be equal to one number or another number, and then 3 and 4 and n, right? And so I can have a superposition of many Waterbergs, and so I can just treat them as different species of particles. And it turns out that this entire construction can be generalized, and what you get is essentially is a form of superposition of Fermi-Dirac distributions, which, when they degenerate, look like ziggurats, like this picture on the screen, right? So you can see these multiple Waterbergs here. The next obvious step is a continuous generalization of this, right? So what I can now do is I can define a kind of hyper distribution function, right? Or Uber distribution function. I don't know what to call it. Or maybe in Paris, it's called the G7 distribution function, right? What's your favorite cab app here? So anyway, so we call it, Robbie and I, hyperkinetics. And, you know, we're trying to, it's, you know, coining new terms is one of the fun things about doing useless things. And so we're trying to convince everybody to adopt this nomenclature. Anyway, so we have this hyperkinetic distribution function P of Q. Remember, Q is R and V. That's the phase space. And so this is so what we now do is we take our phase space density, and we treat it as a random field, and then we construct the distribution function, which is the probability for the phase space density to be equal to eta at position R and V. Okay, so that's, we have these random things, and that's this P describes that. Formally, it's just the average of the delta function of eta minus f of Q. And so if you do that, then now you can think about your system now as being described by all possible forms of the distribution function, and then your natural Shannon entropy of this, or Gibbs Shannon entropy, is just P log P, because that's how you quantify the uncertainty about the complete uncertainty about what the distribution functions will be. So you maximize that distribution, that Shannon entropy. You maximize it subject to constraints, conservation of probability, right? So it has to, you know, the total probability for the distribution function to be equal to something at any position in phase space has to be 1. You ask for the conservation of energy, And you ask also for that constraint that I introduced at the beginning, right? The phase volume conservation, the conservation of the water bag content. Remember this rho of eta, which was the phase space integral of this delta function, essentially. So I called it water bag content. The reason I called it water bag content is because now I have a system of a continuum of water bags, right? And rho tells me how much of each water bag there is in the system. And that has to be conserved as well, because that encodes the conservation of phase volume. So this formalism, I didn't invent this formalism. This formalism comes from, it's French, actually. It comes from vortex kinetics and galactic dynamics. It is associated with people like Robert Sommeria and Pierre-Henri Chavagny, whom probably some of you know. So maybe you know the other two as well. Right. So if you do that, if you maximize entropy, you end up with a kind of a generalized form of the Fermi-Dirac distribution, which means that essentially it's actually, more or less a Gibbs distribution for in this hyperkinetic phase space, where things depend on the phase space and on the value of the phase density itself. And then if you want to find the actual distribution function you're after, distribution function of particles, then you multiply this p by eta and integrate over eta. So it's the first moment of this distribution function. So the reason we call it hyperkinetics is because it is to kinetics what kinetics is to fluid dynamics, right? Remember, in fluid dynamics, you calculate, I don't know, density, for example, right? And what is density? It's the 0th moment of the probability distribution, right? And often to calculate density, you have to calculate the probability distribution itself, because when you start writing equations for calculating density, you find that you have a closure problem, but on the kinetic level, you don't have a closure problem. So here as well, you'll see that will happen. So right. So this is the continuous generalization of that Fermi-Dirac distribution that I talked about. Notice now that we still have an effective temperature, 1 over beta, and we have a chemical potential, but now chemical potential is a function. It's a continuum function of the water bags. For each water bag, there is its own chemical potential, which enforces the conservation of phase volume. So now let me get to the question of, what does it all mean and how do we then analyze it? This is all very nice as a formalism, but then what, right? I mean, you might say, okay, great, and right? So there is another fact from the 1960s, which has been known in galactic, in plasmas is called Gardner's theorem, and in galactic dynamics, I think it's called the Antonov's theorem. Which is the following: if you take, you can ask a different question than I asked so far. Rather than asking for relaxation at constant energy, you could say, suppose I had some initial state, and I was under obligation to conserve phase volume, so there are no collisions, but I can remove energy in some way. And I can ask what is going to be the minimum energy state of such a system, the ground state, okay? So, and I will conclude, if I can find it, I will conclude that at least is an equilibrium, right? And a stable one. It's not, you can't, you can think of all instabilities as extracting energy from a system. And if you cannot extract any more energy from the system, you cannot be unstable. Right? So we call it Gardner distributions. And it turns out that the Gardner distribution is simply this. You take your initial conditions and you move them around in phase space in such a way that the water bags with the largest phase density go to the smallest energies. And then the next ones to the next energies, and the next ones to the next energies, and so on. This is called Gardner restacking in plasma physics. You can visualize it as in your mind as an experiment with, you have lots of fluids with different densities mixed up together, right? You put them in a jar, and you shake the jar, you leave it alone, and you wait for what happens, and then the heaviest fluid will settle down, the next one up, and then so on, and that'll be the stable distribution. So this is exactly what Gardner distribution is. So and formally it's a distribution with the same water bag content as before, but required to have a negative derivative with energy. Okay, so energy the distribution function has to decrease with increasing energy. So why have I brought this up? Well, so first of all, obviously, if the Gardner energy, so this distribution, if I took my initial distribution with some initial water bag content, right? For each initial water bag content, I can derive a Gardner distribution. And it's obvious that if the energy of that Gardner distribution turns out to be less than the energy of the distribution you started with, then the Gardner distribution the energy is less for any initial conditions, and therefore the Gardner distribution is stable, right? Because you can't extract any energy from it. Now, it's obvious that the Lynden-Bell equilibrium, which is in the box, is a Gardner distribution of itself because it does decrease with energy. It's, you can differentiate this in your mind with respect to epsilon and find that the derivative is negative. Now, furthermore, you can prove, and that's, again, it's obvious, but the proof itself is slightly tricky. You'll find it in one of Robbie's papers, which I referred to at the beginning of the talk. You can prove that if the energy of the initial distribution is very, very close to the Gardner energy, that's equivalent to the inverse temperature being very close to infinity. So in other words, Gardner distribution is the degenerate limit of the Lynden-Bell distribution. It's the ground state. So it's obviously the zero temperature state, right? So now non-degenerate in this context means that the energy is much larger than the Gardner energy. So why did I talk about this? Well, this is to do with the, and this is the first result that I will show you that's not from the 1960s, right? This result is from the 2020s. Right, and that's Robbie Eward's result. So what Robbie noticed was that studying classes of water bag content, when I say water bag content of something, this is difficult to think about intuitively, right? I bet you even if I told you, oh, let's look at a Maxwellian, what's the water bag content of a Maxwellian? I'm sure you can derive it, right? But you can't instantly visualize it now that I'm telling you about that, right? So you haven't thought of that before. So it's a kind of a non-obvious quantity. But studying classes of water bag contents is in fact equivalent to studying classes of ground states, right? Because anything with a given water bag content will correspond to a certain ground state, and on some vague level, it is intuitively easier to think of what is the ground state of the system, right? Ground state of a Maxwellian is a Maxwellian. So, right, and so now we can ask the question of universality in the following way: for a typical kind of ground state, what is going to be the water bag content, and what is going to be the what set of equilibria we will then get? So here's an example. So let's take a Maxwellian, right? That's the thing here on top, what I call FG, and let's calculate the water bag content of it. That's that non-obvious thing that I've just mentioned. So I'd like to have this Maxwellian going up to a maximum, which I call eta max, and for reasons that will become clear in a moment, I want to cut it off at a certain minimum, which I'll call eta min. So I don't want it to extend completely to infinity. So the water bag content is this, right? It's this kind of 1/eta times log eta function. So more generically, it turns out that you can show that for a vast class of distributions, the water bag contents always will look like 1/eta times some slow function of eta. And if you accept that for a moment, well, when I say for a vast class, for a class of exponential distributions, actually, right? But that's a fairly vast class. So now you can generalize this, but I won't for now. And so it turns out then that if I then consider cases with energies that are much larger than the ground state, right? So I want to look at systems whose underlying ground state has a certain energy, but which is in fact in a highly excited state. I can go through all this algebra that I showed you before in a certain approximate way and actually derive the distribution, the Lynden-Bell distribution from that water, impose all these constraints, do the integrals and so on. And if I do this, or rather if Robbie does that, as he did in here, in that reprint, it turns out that that you get essentially a universal power law distribution for energies, which is simply 1 over energy squared. So times some non-universal factor that one can study, but we won't for now. So so that's, you can, I'll skip the generalizations of this. I'll say parenthetically that it turns out that no state is fully non-degenerate, that you have to do some work dealing with that, and skipping all that work, I'll simply say, here's the first interesting and a very simple result, which seems to point towards a degree of universality in this nonlinear behavior. So typically what will happen with these distributions, with these Lynden-Bell equilibria, is at large energies, they will have power laws that are 1 over energy squared or not very far from that. And then, so that's true when the energy is very, very large compared to the Gardner energy. And that tail will persist at high energies, while at low energies, you will find a non-universal bit, which is a remnant of the underlying ground state. And of course, ground states can be very different for different systems. So you should think of the Lynden-Bell equilibrium as a combination of a non-universal core, that's related to the ground state, and the tail that depends on nothing. Now, if you start looking at systems with energies that are closer and closer and closer down towards the ground state energy, what will happen is that the core will become more prominent and the tail less. And so, if you looked at an energy that's only just a little bit above the Gardner energy, what you will find is a big non-universal core and then a little universal tail trying to emerge. So this, I think, gives us all hope that some generic things can be said about what will happen. Now, this is why should it be interesting to anybody other than statistical physicists? In fact, I don't know if this is interesting to statistical physicists, but why should it be interesting to astrophysicists? Well, we deal with the emergence of power law tails in cosmic contexts all the time. There's the famous problem of cosmic rays, non-thermal particle acceleration, which have observed power law tails. In the solar wind, people see distribution functions which always look like some kind of core halo structure, some sort of blob in the middle, and then a power law on the ends. These are the potential ways in which maybe you can think of all these things in the context of equilibria of certain types emerging for very general statistical reasons. There are, of course, enormous limitations to this. The 2 main ones are this. First of all, how good is this requirement of exact phase volume conservation? I may say something more about that in what follows. And secondly, of course, you could say, well, are we really dealing with equilibria, or are we dealing with distributions that emerge in non-equilibrium processes, and therefore we shouldn't be thinking about equilibria at all? So I'll leave these questions hanging. You should watch this space on this subject, his space on the archive, or maybe I should say watch this face space. But I want to move on to the in the next 10 minutes perhaps to the next topic on this, which is going to be the following. So how does statistical physics, or rather how does physics generally work? We start with these statistical physical statements about equilibrium distributions. And then typically, if you remember your undergraduate course on the subject, you go on to kinetic theory from statistical mechanics, right? And why do we go to kinetic theory? Because you're dissatisfied with the notion that something is in equilibrium, and that you want to ask, how is this reached? How and how fast in particular, right? So that corresponds to, in mathematical terms, this is called deriving a collision integral. So what does that mean, deriving a collision integral? Or in this case, it's a kind of a collisionless collision integral, in the sense that I don't mean collisions between particles in a Coulomb sense anymore. What does it mean? Well, it means that you want to derive some kind of equation that says d by dt of the mean distribution function is equal to some right-hand side that depends on that mean distribution function rather than on everything. Okay. So, and then equilibria should be fixed points of that right-hand side. Okay, so that's a kind of and ideally it'll be some kind of operator acting on f bar, and in front of it there will be some kind of time constant, or rather rate constant, and you can call it your collision rate or relaxation rate. And if you can derive that, then you can tell people not just where everything wants to be, but also how long is it going to take to get there, and possibly through what states it'll have to go on its way. So how does one do this kind of theory? Well, the starting point is the Vlasov equation that I wrote before. And so what you do is you take this Vlasov equation and you average it. And by averaging, remember what I said about averaging. Averaging means just integrate over space. Okay? So you average it, and that tells you that d by dt of its average is equal to, you can see that, if I average over space, this second term will disappear, and the third term will contain a correlation function between the electric field and the part of the distribution function that depends on space, which I call delta f. So df by dt is equal to d by dv, divergence in v space of some kind of correlation function, right? So it's a, d density by dt equals to divergence over flux, right? The usual kind of story because density is conserved. So now that correlation, again, there's algebra on screen, but that algebra is supposed to work in the same way as sort of graphs and visualizations work in talks about observations and numerical simulations. It's just a visual aid, right? You're not actually supposed to parse it. I'll talk around it. Yeah. I can do both. Generally speaking, it can be both. I can stir it up in some way, but there's also a self-consistent part to do with the distribution function. Yeah. So what's the basic message? The basic message is that the rate of change of the mean distribution depends on the correlation function of delta f. Right? Remember I said that there is a relationship between the question about what is the structure of phase-spaced plasma turbulence and what is the evolution of the equilibrium. That's the relationship, right? The evolution of the equilibrium depends on the correlation function of the turbulence. That's not a new thought. If you thought about how, for example, fluid dynamical problems work, right? I don't know, an airplane flies, the wing feels a drag, it's a turbulent drag. To calculate that turbulent drag, you need to figure out the effective turbulent viscosity. What's the effective turbulent viscosity? Is the correlation function of the velocity field, right? So engineers deal with this all the time. So this is the same thing, but happening in phase space. So in order to do what I have just said, in order to calculate the collision integral, you need to work out the correlation function of the plasma turbulence in phase space. And of course, nobody's done this, and it's hard, and it's possibly even impossible to do. And so I have absolutely no idea what the answer is. Now, what does one do when one has no idea what the answer is? One tries to cut through with some simple, almost certainly wrong assumption and hope that that assumption would be enough. Such an assumption about this distribution function is right there. There's another new coinage in our pursuit of new language with Robbie. We call it the microgranulation ansatz. Sounds good, doesn't it? I mean, anything that has the word ansatz in it already sounds very respectable, and microgranulation. Great. So please adopt it. Now, but it's simply the following. It's simply the following statement. Let's assume that if I correlate the distribution function at point 1 and point 2 in phase space, I will find that it is uncorrelated. Okay, so it's a statement that the correlation function is equal to the delta function, and then I have to put in some Kalugi factor in front, which has the dimensions of a phase volume, and which basically tells me what is the size of the volume in the correlation in the phase space over which there are correlations. Right? So that's the assumption. Now, if you look at what that does to this calculation that's in this line, you're in for a terrible disappointment. So disappointment is the following. So if you have, while I was talking idly, worked through this algebra, you might have noticed that the thing on the right-hand side in that equation only depends on the imaginary part of the correlation function between the Fourier transform delta f. If you haven't worked that, it doesn't matter. Just accept it. It depends on a certain imaginary part, which is the same as a part that's not symmetric with respect to changing the variables. But delta function changing v and v prime, so the 2 points at which I'm measuring the correlation. But the delta function that I've assumed is symmetric, and so if I plug this assumption into that right-hand side, I get 0. And so that's no good. And what that means is that actually the evolution of the equilibrium will only happen if certain correlations do develop. Okay, and so one has to do a little bit better and calculate the development of these correlations. How does one do this? So this is called kinetic theory of phase mixing, right? So now you have to. What this says is that you can't just get away with knowing nothing at all. You have to know something. So how does one work out the kinetic theory of phase mixing? I'll simply sketch it on a very, as it were, coarse-grained level. The starting point is, again, the Vlasov equation. Remember, last time what I did is I averaged the Vlasov equation. I got the equation for the distribution function. Now I'm going to take that average, subtract it from the Vlasov equation, and write an equation for delta f. Right? So that's the part of the theory that describes my turbulence. And what will it have in it? It'll have 3 things. It'll have phase mixing, this term here, which in Fourier space looks like this. It'll have a interaction between the electric field and the equilibrium distribution function, right? So that's a source of fluctuations of delta f, right? So there's an easy fluid mechanical analog of this. Imagine that I have a field of some concentration, like concentration of a dye in water, or say temperature in some fluid dynamical system. And imagine that I stir randomly, and then I impose an overall gradient on the problem. Say there's a temperature gradient across the box, and I stir. That will create temperature perturbations, right? Because there will be a u dot grad of the mean gradient. So this is the same thing except in phase space. Because the distribution function has dependence on velocity, that will stir up fluctuation. So that says that, and remember, distribution function and velocity is never uniform, right? Because it has to have an energy scale, right? There are no particles with infinite energies. So and that means no system that is inhomogeneous in space can remain without the delta f. So that's this. And finally, there is the interaction of the electric field with delta f, which is that's the mode coupling. These are the things that I referred to at the very beginning of my talk. So what you can do is, again, remember, if you can't avoid doing any theory at all, the next thing you do after that is perturbation theory, right? Because that's the only thing that we actually know how to do, right? We know how to Taylor expand. And so you can do perturbation theory. What you can do is you can throw out the nonlinearity, you can take your delta f and try to evolve it without the nonlinearity. It's a linear system, so that can be done. So just basically throw out this last term, and so you can evolve it, work out the correlation function this way, right? And work out the asymmetric part of it. And it turns out that if you go through all that, so then there's a nuance. You have to start somewhere. So you assume some initial condition, and then you evolve your kinetic equation in neglect of nonlinearity from that initial condition. And then you work out the correlation function of what you have evolved. And that will depend on the correlation function of the initial condition. And then what you do is you use that assumption that was based on knowing nothing, the microgranulation ansatz. You now apply it to the initial condition. So in other words, you take your initial guess for what the distribution function is and let it evolve linearly a little bit. So conceptually, what it's a bit like saying, well, basically, I can surprise my system at any point in its evolution, pick out whatever I have there, assume that it's all uncorrelated, and then let it go for a little bit more and pick up the correlations. And once I pick up the correlations and stick it into the algebra and turn the crank on the algebra, what one ends up deriving is a set of collision integrals, and it turns out that with luck and some competent theoretical action, you get collision integrals which have H theorems and fixed points, and the fixed points are the Lynden-Bell equilibria that I derive statistical mechanically. So this is, if you like, so this is done again in Robbie's paper that's quoted here. So, but it goes back. I mean, to be fair, Robbie and I were not the first people on this domain. There is a whole bunch of different people who have worked on various versions of this collision integral. Most of them actually in the galactic dynamics context rather than in plasma physical context and context. So some of it goes back into the 20th century. Anyway, the point that, so this is a program which is basically, this is what Boltzmann did for Maxwell and Gibbs, right? So you have equilibria that maximize entropy, and then you say, how is this reached? You work out some dynamical way in which this is reached. So this has been achieved. I will skip if anybody wants to know what these things look like, I'll show you, but I won't, since I should be finishing up. Now you might say, why is it reasonable that you should use these you should do what I had just described before, that you could take these initial conditions at any given point in the evolution of the system and assume that they're uncorrelated in space and velocities. Well, actually, the only way this can be reasonable is because, in fact, you haven't neglected the nonlinearity. It's because you actually say, what I want to expect is that I will take any initial condition, I will evolve it linearly, it'll evolve those correlations that produce the collision integrals. And then I'll assume that the nonlinearity will take over and mix everything up, right? And return me back into this uncorrelated state. That's the basic assumption there. And the big question is whether the nonlinearity does anything that itself changes the form of the evolution of the mean distribution function and changes the ultimate universal equilibrium. Right. I think since we are 2 minutes before the cutoff, I've got slides on how to do that with nonlinearity and what might possibly happen in a nonlinear case, but I won't go through them. But you're welcome to ask me, and we can continue this conversation now or later or whenever. All right, so I'll stop with this declaration of what the program is, and so you know what you're missing there. But I will leave. I will leave with this last slide, which is a set of questions that astrophysicists might want to discuss in this context. All right, thank you.
Thank you very much. Is there any question? Oh, actually, we had many people in remote, so please don't hesitate to raise your hand or ask question. Maybe we'll make it short.
Oh yes, there are 15 people in remote.
Actually, there were more people before.
Maybe we should ask them to show themselves.
Oh yes, please turn on your video if you want.
Can we see you guys? Even though you're in 2D, we're you're still welcome.
So thank you for this nice talk. I have a question. So I think you didn't mention in your talk the term Landau damping. And recently I became completely confused because according to what I understood from Binney and Tremaine, Landau damping or violent relaxation is something different from phase mixing. But recently I heard from several places that Landau damping is the same as phase mixing. And your talk gave me also this impression. So what do you think I should think of it, or what is the connection between the two processes?
Well, like always with these dichotomies, right? Both statements are true. Landau damping is the same as phase mixing. Yes, Landau damping is not the same as phase mixing. So now Landau damping is this. You put into your plasma some electric field, dependent on space, some electric perturbation, collisionless plasma. You let it go, and you will find that that electric field will decay exponentially, right? So, and that can happen at a rate that's entirely independent of collisionality in the plasma. So it happens in collisionless plasma, right? So that there is a formal theory of it, which was worked out by Landau. That theory was, of course, mathematically entirely unsatisfactory, and so it took a concerted and largely French effort to sort it out and turn it into a rigorous mathematical theory. And indeed, Cédric Villani, who was, before he was going to be mayor of Paris, he was preoccupied with the iniquities of Landau damping, and so he got a Fields Medal for his efforts. So now, mathematically, Landau damping is a decay of the electric field, and therefore, because the electric field is determined by Poisson's law, it's the decay of the density perturbation, right? So now you can ask the following question: well, why does anything decay in a system that's collisionless and therefore Hamiltonian, and everything has to be reversible? Sorry, everything has to be reversible, and so on. And the reason is basically phase mixing. It's because you take your perturbation. Remember my picture at the beginning where I had a blob in phase space, and then there was that blob was being sort of teased out and mixed and so on. So imagine I start with some perturbation and then I mix it. When I mix it, it becomes very, very chopped up in velocity space. Now, what is the density? The density is the distribution function integrated over the velocity space. So if it becomes very chopped up in the velocity space and ever more chopped up, that integral becomes smaller and smaller because most of it cancels. It doesn't mean that delta F disappears, but it does mean that delta N density disappears. And that's what Landau damping is. It's this disappearance of the density. So in that sense, the Landau damping is the same thing as phase mixing. It's not the same thing as the phase mixing in the sense that there can be certain fluid dynamical circumstances. By fluid dynamicals, I mean certain types of physics that happen at the level of low moments of the distribution function. You can create situations in which the connection between the density moment and other moments is, for example, a lot weaker than generally the phase mixing would imply. And so you can actually construct situations when Landau damping is extremely slow, even though the phase mixing is very fast. So in that sense, it's not the same thing. So an obvious example of that on the physical level rather than on mathematical level is the following. So Landau damping energetically involves taking energy out of the electric field and putting it into particles, obviously, right? Because if it disappears from the electric field, where's it going to go? Into the kinetic energy of the particles. And mathematically, in Landau's theory, it works via the fact that there is a resonance between particle velocities and the phase velocities of waves. So if you inject into your system waves that have such large phase velocities that only very few particles can match that, phase velocities sit somewhere in the tail of the distribution function, that will produce Landau damping that happens exponentially slowly. Okay, so that's the sense in which it's not quite the same. Sorry about the long answer, but I hope this makes sense.
So maybe a last question.
You're using Boltzmann equation as for dynamics of the distribution. Now, usually in physics, it is a Fokker-Planck equation, which is used for the variation of probabilistic distributions. Now, what is the difference? Is there any, because a priori at least in the quantum field theory, you can obtain the classical Boltzmann equation from the gap equation. Now, I don't know if in your approach, is there any similarity or?
So I think we need to decide what we mean by all these names. So when you say Boltzmann equation, presumably what you mean is a kinetic equation that describes particles that stream but also collide, right? So Boltzmann equation is the equation with the Boltzmann collision integral on the right-hand side, or do you just mean df by dt plus v dot grad f?
What you are using, you are putting the collisional part equals 0. Therefore, it is not collisional.
Okay.
But you consider a field. Therefore, in some way, you have the interaction.
Yeah, it's the interaction with the mean field. So the particles interact. So within that approach, the particles interact with the mean field created by all the particles, right? Rather than with each other binarily. It's a kind of a COVID approximation to dynamics. We remember how we all sat at home and never interacted with each other in a binary way, but we all interacted with the society via TV, right? So that's E dot df by dv, right? So that's the mean field approximation in that sense. So now, so we call what you call Boltzmann equation, I think we call Vlasov equation in plasmas. That's the left-hand side of that thing. So the collision operator in plasmas is a Fokker-Planck operator because it describes Coulomb collisions are glancing collisions. They are accumulations of small deviations. So it is diffusion plus drag. So that is a Fokker-Planck equation. The collision operators that Robbie and others have derived based on the procedure that I have just described to you are essentially Fokker-Planck operators as well. So in hyperkinetic space, though not in the kinetic space. What the true collision operator is, if you include nonlinearity and all this, we don't know. It may not be a Fokker-Planck operator. In fact, well, it may not be a Fokker-Planck operator. So that's.
Thank you very much. We will stop here because it's a little late. Professor Schekochihin is still here all the afternoon, I think. Yeah. And so please feel free to probably to come. You will work with Jean-Baptiste.
I'll be around.
Thank you again.
Right.